now that we know how an alternating series, error works, you just kind of truncate it, and whatever the next term is, that's your error, max error. We're going to now talk about how well does like 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial approximate a cosine wave, right? So we can actually look at a picture of this and understand the question better, okay? And let's go ahead and give one more given here. How about between x equals 0 and pi? So we'll go and write that in too, okay? Between x equals 0 and x equals pi. Okay, so let me pull up my grapher and you can see exactly what this question is asking. Okay, so I need a cosine wave. I'll move it a second. Okay, there's a cosine wave, right? And then I have this Taylor polynomial that's supposed to approximate the cosine wave. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And this is going to show up in blue. You can see that this is actually pretty good in the middle. See how well it hugs the curve? Not bad. So now I'm going to go ahead and switch my units to pi's real quick. Okay, so you can see what happens here. Actually, the curve does a fairly nice job, but as you get towards pi, there's a gapper right there. See the gapper? That's like gap. So that gap right there, I'm curious how big it is. Or if I can't get that exactly, I would like to know roughly how big it is. Or what is the biggest it could be? That's another way to ask the question. So what is the gapper, or what is the biggest that gapper ever could get? Okay? So to find the answer to that, you have to use this horrible formula here. This is called the Lagrange remainder, or the Lagrange error bound. So let's title that. The Lagrange error bound. Okay, before you completely freak out, it actually looks a lot like what we did yesterday. So here's what we did yesterday. We had an alternating series. Okay, let me do a quick example of that again. I think this is the example I showed you yesterday. Let's say you have this alternating series, n equals 0 to infinity, and it's just simply 1 over negative 1 to the n over n factorial. The first term is 1 over 1 factorial. The next term is 1 over 2 factorial. Actually, it's a 0 first, and then 1, sorry. And then the next term is 1 over 2 factorial, and this just goes on forever, right? Minus 1 over 3 factorial, plus 1 over 4 factorial. Let's say that you took the first 5 terms, even though this really does go on forever, you take the first 5 terms. What is the error in using just the first 5? The answer to that is, it is the 6th term. So the 6th term here, 1 over 5 factorial, that is 1 over 120, is your maximum error. So we were saying this yesterday. It's interesting that the next term represents how off you are at the worst possible scenario of how off you could be. Okay? So the next term is your error term, you can say. The same thing is true here. If you look back at Lagrange's, Taylor's polynomial formula, right? I'll write it again at the top of the page. Maybe you should too. Lagrange's formula looks a lot like the next term of the Taylor. Watch. Here's a Taylor polynomial, or Taylor series, I mean. You can write n equals 0 to infinity, right? And it's the nth derivative at a over n factorial times x minus a to the n. See, that's your Taylor series. Look now at the yellow. That's really just kind of like the next term. Yeah? You've got n plus 1 derivative instead of n derivative, right? You've got n plus 1 factorial instead of n factorial. You've got x minus a to n plus 1 instead of x minus a to the n. It really is kind of like the next term. So this is very similar to what we just did with alternating series. Almost easier to memorize. The alternating series error is the next term, or the first unused term. The Lagrange error is just the next term in the polynomial, except there's a z there. Okay, so one thing you need to know before we do any Lagrange error-bound problems is it doesn't actually give you the error. It gives you the max error. There's a difference. If I told you that I knew the error, bear with my logic here. If I said my answer is 0.14 and the error is 0.2, that means the answer is 0.34. You know the exact answer. Why are you reporting error? See? So I'll say that again. If I said the answer is 0.14, the error is 0.2, that means I already know the answer. It's 0.34. I'm getting you my answer and the exact error. That means I know the exact answer, you see. So don't think that we're actually getting the exact error. We're getting a maximum possible error. That means what we get for these problems is just the worst case scenario of what our error is. Our error could actually be less than that. All right? Okay. So let's say I asked you, hey, I'm adding up a series and I got 0.444. What do you suppose my maximum error is? You might say 1,000. I think you're off by no more than 1,000. You're probably right. You're probably right, I'm off by no more than 1,000. Can you give me something smaller? Something that just sort of makes me feel good about my answer? Okay, so we're trying to find the smallest possible answer to the maximum error question. Okay? A little hard to word. Okay, let's try the problems. So they are a little tricky. So let's take a look at the first one. It says, determine how closely the 9th degree Taylor polynomial for e to the x at 0 approximates the true value on the interval 1.8 to 2.2. I'm going to try to make this as easy to understand as I can. Let me take out some of these extra blanks here. So I have all of my problem on one screen. Okay, good. All right, so let's write down our max error formula first. So the max error should be the absolute value of the 10th derivative at z over 10 factorial times x minus 0 to the 10th. Why? Well, this little a, the at x equals 0 means a is 0, okay? And the fact that I'm using the 10th derivative is because it says the 9th degree Taylor. So I'm finding an error, so I should be using the next derivative, see? Okay, so now we're going to try and fill this in with numbers, okay? We have to fill in the z and the x. All right, so first maybe we should talk about the 10th derivative. So what exactly is the 10th derivative of e to the x? Fortunately, it's just e to the x, isn't it? Okay? Yes. So basically, this is an e to the z over 10 factorial, and this is just x to the 10th. And now I'm forced to pick an x somewhere between 1.8 and 2.2 that would make this x to the 10th as big as possible. Okay? So this is where you have to do a little critical thinking on these problems. You can pick any x you want between 1.8 and 2.2, but your goal is to make this as big as possible. So would you pick 1.8 or 2.2 or something in between? 2.2 has the largest 10th power out of all the numbers between 1.8 and 2.2. So on this problem, we will pick the right endpoint because it maximizes the x to the 10th. The 10th derivative of e to the x is still e to the x. Because it's f, the 10th derivative at z, not the 10th derivative at x. Okay, so I am picking the largest x I can because that will make x to the 10th as large as possible. So this is 2.2 to the 10th. Probably don't really need the absolute values here. Question? Sure.
2.2.
Well, I'm trying to make this expression as big as possible. I don't want to underestimate my error, right? If somebody says, what's your error? You should probably give them a conservative estimate. Like, give them the biggest thing you think of, right? I'm off by no more than blah, blah, blah. Okay, so we're trying to maximize this expression. We can only pick x's between 1.8 and 2.2. So I chose the 2.2 because I thought that would max this out. Does that make sense? Okay, now it's time to pick a z. Z is a little bit different from x on most problems. But on this problem, it's almost the same thing because basically what we're saying is z should be chosen between the center of convergence, okay? So I didn't say that yet, but I'm saying now. Z is a number between the center of convergence and your x that you're evaluating. So that would be from 0 to 2.2. Pick an x. Pick any x from 0 to 2.2. But your goal, again, is to maximize e to the z. So if you're trying to pick a z that's between 0 and 2.2, right, you might as well pick 2.2 again. You're trying to make e to the z as big as possible. So this is just e to the 2.2. So in this problem, the z and the x were actually the same. And this needs to be typed. Okay, so let's get that done. And I got 0.0066. Okay, so I'll just put my answer on the left. The max error is 0.0066. Okay, and then I have one small regret here with something I typed, which I'd like to correct right now before we move on. Any questions so far? Yes.
Why did we do it all right there if we had the whole?
I don't know. I forgot it was fill in the blank. Let's fill in the blanks. The 10th derivative is still e to the x. Since e to the z is only increasing on any interval, f to the 10th of z is just e to the z. Right? And the x value that maximizes this expression, and we're going to use e to the 2.2, actually, to max out the e to the z. And for the x to the 10th, if we have to pick an x that maximizes this, we're going to pick 2.2 again. So this becomes 2.2 to the 10th. And then we just kind of plug that into our Lagrange remainder. So we're going to be plugging in 2.2 to the 10th and e to the 2.2. Was there more blanks? I think that's it. Okay, answers at the top there. Thank you. Before you move on, I did notice this very, very, very tiny error in my typing right here. This should be an equal sign, not a less than sign.
So max error is less than or equal to that, and then
This should say max error is that, not max error is less than or equal to that.
and then so
You can put the error is less than or equal, or you can put the max error is equal. Those are equivalent statements. To say my max error is 5 is the same thing as saying my error is no more than 5. So, because I put the word max here, I should have used it equals. Sorry about that. Everybody fix that in the notes? Okay. I think I'll change it here for next year's students. Maybe erase that. That way I won't have to explain that next time too. Okay, let's go down to this next example. Use the Lagrange error bound to determine the max error that the 99th degree Taylor polynomial gives in approximating the true value of cos x at x equals 0 on the interval from negative 0.5 to positive 0.5. Okay, so this particular lesson, you guys, I have searched the internet for examples. I've searched the internet for good videos. I have looked long and hard to come up with this lesson. So if you miss this lesson, if you're not paying attention, you're going to have a very hard time remediating yourself on it. I honestly find this to be one of the hardest topics to research of all Calc BC. There's very few good examples out there. I typed up as many as I could, and so make sure you don't miss this. All right, this one's a little different. The z and the x, for example, when we get toward the end, they're going to be a little different. Okay? So let's just see if we understand the question. We're doing cosine x, right? That just looks like this, right? we've got a 99th degree Taylor polynomial. Now this is only between negative 0.5 and positive 0.5, mind you. Okay, the whole thing happens between negative 0.5 and positive 0.5, it says. A 99th degree Taylor polynomial hugs the curve so well that it actually hugs all the wiggles out to 48 wiggles on the right and 48 wiggles on the left. Okay, so this thing like does 49 wiggles actually in each direction. So if you can picture the actual curve, it's amazingly good fit for a cosine. Here's cosine, you know, like that. This polynomial actually fits cosine all the way out to almost the 50th wiggle, and then it diverges apart. You see? You guys understand what I'm saying? And here we are zooming into the very center of it all to see how well things fit. Well, you can expect an extremely tight fit. Okay? All right. So there will be some error because you're trying to model a polynomial onto an actual cos wave, which is technically impossible using even 99 terms. You have to use an infinite number to really do it. Okay, so what I'm saying is the blue and the red are extremely close together. We would like to find the largest gap that could exist. Okay? Okay, so max error, such a dork. Okay, the maximum error should be the 100th derivative at z over 100 factorial times x minus 0 to the 100th. Excuse me. Okay, why 100? Because we're doing a 99th degree Taylor. And then you're going to look at 100th, which is the term after 99, right? Okay, so it's x minus 0 because it says at 0. So that's how you determine that. This is your a, and this is your a. Okay, so before you freak out, what's the 100th derivative of cosine? It's cosine, that's right. So nothing to be scared of there. Cosine, every fourth derivative is back to cosine again. So imagine doing that 25 times. Okay, so we would like to go ahead and fill that in. We're saying that this is really just cos z. Then there's a 100 factorial there. And then there's an x to the 100th here. And all this is absolute value. Now it's time to pick an x. Okay, and a z. Let's pick z first this time. Last time we picked x first. Z is any number between the center of convergence and the largest x we have. Or another way of thinking this is let's just try to make cos z as big as possible. Let's just try to make cos z as big as possible. Okay, so what might we plug in for z? What do you guys think?
0. Makes it 1. It's the highest it goes.
Yeah, so there's a couple ways of thinking about this. You're allowed to pick any number you want between 0 and 0.5, right? But cosine is one of those functions that sort of falls off, right, as you leave 0. So it's a little different from the last problem. As you go to the right, you actually lose value. So cosine z should max out when z is 0, actually. So that's what we'll pick for z. So it maxes out at z equals 0, making this a 1.
Wait, why does it max out when z equals 0?
Well, cosine is just a little different from like sine and e to the x. It actually starts off by falling, right? So if you're going to go from 0 to 0.5, you will achieve the largest cosines when you're at 0.
Oh, okay.
See that? That's why I wanted to do this example. It's very tempting to plug in 0.5 like we did last time, you know? Okay, but for x to the 100th, if we want to max out x to the 100th, which x value are you going to want to use from your domain?
You can do either, can't you?
Yeah, it doesn't actually matter, but you're going to want to pick an endpoint because you're trying to make x to the 100th a large number. So don't pick 0.
Well, no, like, it doesn't matter which endpoint you choose.
Yeah, you pick either endpoint in this case, because it's an even function. So you can pick 0.5 or negative 0.5. Either way, that x to the 100th will max out. So this is 0.5 to the 100th or negative 0.5 to the 100th. Okay, so what you need to type is, somehow you need to type this, 0.5 to the 100th over 100 factorial. The problem is most of our calculators will overflow with a factorial this large. So you have to actually maybe go on Wolfram Alpha to get the correct answer here. Which I did. So to save us a little time, or if you have the app, you can. Just type that.
Give me a
By the time I find the page and the answer, you'll probably have the answer anyway. It's a ridiculously small answer. The max error here is Did you get it?
8.452 times 10 to the negative 189.
Yes, right.
Wolfram Alpha's a genius.
Yes, it is.
I just typed it in.
Anyway, that's a tiny error. And so the max error will happen when x is 0.5 or negative 0.5, doesn't matter. 0.5 to the 100th over 100 factorial is 8.453 times 10 to the negative 189, aka no error. Okay? Pretty much nothing. Okay, let's go to our next example. This one is actual AP test question, so it's definitely worth our time. And it doesn't mean it's harder, it's just a little different. Like, I thought it was really clever how they wrote the question. First things first, they did not actually set up a formula for you. Like, they didn't say, here, find x and z. You know what I mean? But if you look closely, what does this even mean? Here's what it means. F is this function, right? P is a third degree Taylor. That means that P is supposed to be kind of a model of F. So P models F. You understand? So we wouldn't expect much error. And if you look closely at what this is asking for error. This green thing right here is error. To say that the difference between the function at 1/10 and the Taylor polynomial at 1/10 is no more than 1/100 is the same thing as saying max error is 1/100. Okay? So this statement is basically, what you see right there is just this. The fourth derivative at z over 4 factorial times x minus 0 to the fourth is less than 100. 1/100. This is what it's saying. The error is less than 100. So at first you might not see that. You might not look at that and say, oh, that's what that means. That's just error. Sure it is. F minus p. That's the gap. The gap. See? The gap's less than 100. Lagrange remainder is less than 100. Okay, so we just jump straight to this. And now we just have to kind of figure out what x is and everything. Well, it turns out actually on this problem, they're actually giving us x. X is 1/10, you see. So that's a little different. That's the way the AP test is. They always give you the wrong stuff. You know, like you do your homework problems in the book, you get to the AP test, they're actually giving you different stuff. They don't give you, you know, the A always, and they ask you for x and z. They give you the x and ask you for A or z. Or they do all sorts of crazy things. Okay, we still need to work on this. So here is what we have so far. This is just a 24. This is just 1 over 10 to the fourth. So you can pull out a 1 over 24th, 240,000. Or let's just write it as 24 times 10 to the fourth, because it's probably going to reduce anyway. Okay, so here's where we have to do a little more work. what is the fourth derivative at z? So we're going to have to play around with this. So let's give it a try here. We know that the function is sine 5x plus pi over 4, right? F prime would be 5 cosine 5x plus pi over 4. I just took the derivative of the inside too, right? F double prime would be negative, and it would be 25 sine 5x plus pi over 4. And the fourth derivative, or the third derivative, would be back to cosine only negative this time. So negative 125 cosine 5x plus pi over 4. And then the fourth derivative is positive again, and it's 625, and it's sine, and it's 5x plus pi over 4. Okay, so that was kind of a pain, but basically what we're saying is that this term, this f fourth derivative z thing, is actually this. It is sine, it is 625 sine 5z plus pi over 4 is less than 100. So it looks like we have one more thing to do maybe, and that is find a z. Oh man, what are we going to pick for z? Give me 1 second. I have to remind everybody where we pick our z's from. Z is a number between the center of convergence, 0, and the largest possible x. They didn't give us an x domain this time. They actually gave us an x, 1/10, right? So I guess z is some number between 0 and 1/10. But here's the problem. I don't know what to pick. I do not know what to pick. Do you know what we might want to do with this problem? Yes.
You approach it like you'd multiply 1/100 times the 24 times 10 to the 4. So it'd just be end up being 24 times 10 to the second.
Oh, just try to like solve for z here?
Yeah. Is that not?
Well, the problem is we're supposed to pick a z that maximizes this problem. We're supposed to pick our own z, not solve for z. You guys understand? We're trying to pick our own z, not solve for z. Okay, so bear with me here. Listen, let's say that I work really, really hard to try to maximize this. So I decide, I'm going to pick z equals 0. Well, that gives you sine pi over 4. That's pretty big. It's 0.7. Okay? And then I said, no, hold on. Let me try z equals 1/10. That's allowed. That's like the other extreme. Ooh, that's going to give me something a little bigger, maybe. But listen, let's just say we don't do any of that. Okay? What's the biggest sine can be? 1. If this statement is true, when sine maxes out, then who cares what z was? Picking a z would only give us something smaller anyway. Okay, so it's kind of a sophisticated argument. But we're saying that we're just going to let sine max out to 1. If that's the case, we could take this, 625 out here. If we just let z be something that maxes sine out, we're going to get this statement. This is just 1/384. This is just going to be a 1, is less than 1/100th. This statement is already true. 1/384 is less than 100. 1/100th. It's already a true statement. But you might say, well, hold on, Mr. Shore, I'm not sure there is a z between 0 and 1/10 that will make this reach pi over 2 and make sine max out. You're probably right, but that's beside the point. The fact that making this a 1 still gives us a true statement to 1 produces a true statement already. Why would you bother with that? So this is what the AP graders actually expected. They expect you to get to this point and say, I'm not finding Z. This is 1. That's 1, the biggest. This statement's already true when this is at its max. If I try to pick a Z, this would just be a little less anyway. Then it would be even more true. So it's true already. Stop the argument. Done.
What? Wait. You just
I know, it's very sophisticated. It's a very sophisticated argument. Let's listen to it one more time. Okay? You can try to maximize this as much as you want. Okay? You can try to pick a Z between 0 and 1/10 that makes this as big as possible.
Oh, yeah.
After all your efforts, you'll find that this is less than this.
Yeah.
But this is less than this, even if I just let sign be una. So why bother with all that Z garbage? You see it now?
That's true, yeah.
It's a subtle argument, for sure. Why maximize sine 5Z plus pi over 4 when you can just consider maximizing sine? If the statement's true, you're done. Okay, so there is the proof that we've got something less than 1/100th. Interesting argument. It's a tough one. I doubt very many people got a 9 out of 9 on that free response problem. You know? Okay, this is the last example I want to show you for chapter 9. It's not even 1994, it's 1999 I found out later after typing this, so it changes to a 1999. And there is actually a part C to this problem, but I put it on the study guide instead. Or I made something kind of like part C for your study guide. This problem is a little bit easier actually. So let's just run through it. First thing is, we know that a Taylor polynomial about x equals 2 will always look like this. Okay? This is a Taylor polynomial centered at 2. This should be at 2, this last, right here, I'll write it in red, in case you already copied it. This is a Taylor polynomial centered at 2. Okay, that's how you build it. Technically, with the dot, 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 it's called a Taylor series. We were asked to write a third-degree Taylor polynomial. That means we would actually stop when we hit the third power of x, which has already happened. So I'm going to erase the dot, 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 and I'm going to go back over here and change this to P3. This would actually be called P3, or some people call it capital T3. Whatever you want to call it, it's not truly F. It's sort of an abbreviated form of F. All right? I'll use P3. Okay, so this is P3 of x. And this is our polynomial. The only thing is we haven't put in these givens. So look at the givens they gave us. This is interesting. They gave us the f of 2, the f prime of 2, the f double prime of 2, and the f triple prime of 2. So those are just numbers. -3, 5, 3, -8. Let's put them in. So we have P3 of x is -3 plus 5 times x minus 2 plus 3 over 2 factorial times x minus 2 squared, and then minus 8 over 3 factorial times x minus 2 cubed. There is your Taylor polynomial, and that's your first answer. So I imagine they would probably give you like 2 or 3 points out of 9 for getting that. If you want to, you can reduce, like the 2 factorial is just 2. The 3 factorial is 6, of course. So I'm going to go ahead and tidy that up a little, guys. Obviously, 3 factorial is just 6, so I'll just write this as 4/3. And who writes 2 factorial? 2 factorial is just 2. So it's really uncool to write 2 factorial. Okay. They also asked us to do something else, so don't miss this. I almost missed this. They're asking 2 questions in one. It says, and use it to approximate f of 1.5. Okay, so I almost missed that. Actually, first period I skipped right over that. I didn't even see it. But basically, f of 1.5 could be approximated by finding P3 of 1.5. And I typed it into my calculator earlier. Let me go and steal my answer from up above here real quick. Negative 4.9583 repeating. Okay, so we'll actually need this number a little bit later in the problem. Okay, so that'd be like full credit. I bet you'd get like at least 3 points right there out of 9. Okay, the next thing says, the fourth derivative of f satisfies the inequality. Fourth derivative is always less than or equal to 3. Okay, use the Lagrange error bound on the approximation to f of 1.5, as we just found, to explain why f of 1.5 couldn't possibly be negative 5. What an interesting question. We're trying to prove that f of 1.5 could never be negative 5. All right, so here's what I would do. I'm going to set up the Lagrange error bound with the fourth derivative, because we did Taylor polynomial degree 3, which involves 3 derivatives. So we're going to go like this. The fourth derivative at z over 4 factorial times, and it should be x minus 2, right, to the fourth. This is my max error. All right, let's go ahead and plug in what we know. Ooh, what do we know? We do know from the instructions that the fourth derivative is always less than or equal to 3. So if we're trying to maximize this expression, I think we should put a 3 here where it says fourth derivative z. Because we're trying to create the largest expression we can. That's always our goal, okay? Try to create the largest thing you can without being ridiculous and saying 1,000, okay? So let's go ahead and say it's always less than or equal to 3. Let's make that a 3. Let's max it out. So that's a 3. And then bear with me here. How are you going to max out x minus 2? Would you want to pick 1.5, or would you want to pick 2? Which one would maximize x minus 2?
1.5.
The 1.5 will, right? So don't pick 2. You're going to get an error of 0. That doesn't mean anything. Pick the other extreme. Let's put in the 1.5er right there. Okay, so a little bit of critical thinking on that phase. But this just gives us basically 3 over 24. And this is a negative half to the fourth, so it's a 1/16. So you end up with 3 over 384. And 3 over 384 is 0.00718, sorry, 81. 0078125. What is this number?
Wait, why didn't you simplify it?
What do you mean, why didn't I simplify it?
Like 3 over 24 is 20.
Oh, you could. 3 over 384 simplifies to 1 over 128. Is that what you're saying?
Yeah.
Sure. Which is 0.0078125. What does this number mean? This is like your max error. Okay? So going back to what you said back in part A, we said earlier, that f of 1.5 is approximately p of 1.5, which we calculated earlier to be negative 4.9583. Right? Now, if I have an error of 0.0078125, I could either add that or subtract that to this negative 4.9. But even if I subtract 0.0078125, yeah, even if I subtract this off, I get what?
Negative 4.96, blank, I didn't get the rest.
Yeah, it's like negative 4.9661458. This is the least it could be. This is the least value. Or you could actually write it as the minimum that f 1.5 could be is this, which is definitely not negative 5. It doesn't quite reach low enough to be negative 5, and that's what we were trying to prove. We were trying to show that this could never reach negative 5. It got close, but it couldn't be possible.